Good afternoon, everyone. My name is Xinjia Hu, and I am a ESR of the CAFE project. And I'm currently working in the Max Planck Institute for the Physics of Complex Systems. And I'm supervised by Professor Holger Kunz in MPIPKS and co-supervised by Dr. Jan Einschner from Munich Reinsurance Company. And since during my PhD period, I always work on the ENSO related topic. So today I'm going to give a general presentation on the El Niño Southern Oscillation and its teleconnection. And also this presentation will cover two of my major research work during my PhD. And so I think that most of you may know that this year we are experiencing a La Niña, and it is still continuing. Because you could see from this left figure that the sea surface temperature anomalous during the last 4 weeks from NOAA. And it's very obvious that the La Niña is continue. And also from this spatial pattern, we could see that the negative sea surface temperature anomalies have strengthened in the eastern equatorial Pacific. And also, I think that most of you may experience the extreme weather events in the summer. And you could also read a lot of news from the social media that a lot of regions in this in the summer are heated by the extreme weather events. And so it is normal that we could suppose that the La Niña is, except for the climate change factor, that have some impact on this. And from the WMO, they predict that it is very likely that we will have the consecutive La Niña winter. It means that this La Niña condition, which starts from 2021, that will continue in this winter. And so it could be the triple dip La Niña of the century. And from this figure, and this is the historical recording of the previous La Niña events since 1950. And we could see that some of the La Niñas that they disappear in the next summer, and some of them last for 2 years. And there are two of them, those in the steep blue curves, that they last for more than 2 years and last for 3 years. So if the La Niña continues in this winter, we will have the third 3-year lasting La Niña event. So it is very probably by the forecast that we will experience in this winter. But however, when will this La Niña decay to the neutral phase is still very uncertain. So from what I mentioned in the last slide, we could see that for the La Niña events, usually it can last for more than 1 year. And it is one different feature that is different from the El Niño. Because for the El Niño, usually it can decay in the next summer. And but for the La Niña, it can last for 2 years or even 3 years. So even we say that the El Niño and the La Niña, they are the two opposite phases of the ENSO phenomenon. It still has several asymmetry of this phenomena. And so what I just mentioned is the duration of this asymmetry feature. And also this asymmetry is reflected by the spatial structure, amplitude, and the seasonal evolution. And all these asymmetry features can lead to the differentiating in the teleconnection and the predictability. And so I think that it's very easy to understand, because if the spatial patterns of the sea surface temperature warming or the coding is different, then it can cause the different atmospheric circulation and lead to the different teleconnection, and also for the other three. And also for the predictability, that if you predict the El Nino in certain method, it cannot easy to directly convert to the prediction of La Nina. And also another feature of the ENSO is its diversity. And it's also what I just mentioned, like the spatial spatial distribution, because you could say that these figures are the Hofmüller diagram of the sea surface temperature anomalies, and the y-axis is the time, and the x-axis is the longitude. And it shows that how the sea surface temperature anomalies develops in the tropical Pacific region. And we could see that for their distribution and the magnitude are quite different between these four groups. And so it is, so we see why this matters, because it's related to the different type of teleconnection. And another interesting and promising question is this ENSO diversity? Could be that, for example, the CP ENSO is a distinct phenomenon, or it's just a different expression of the ENSO phenomenon. So it's still under debate for this question. And here are some indices for the ENSO, and they can also reflect this ENSO diversity, because as we know that usually there are two types of ENSO, depend on the warming or the cooling region of the sea surface temperature. And the different authors that they define this different indices. And when we conduct the ENSO research, when we mostly rely on these indices. And then I will come to the first topic, is the combined impact of the ENSO and Antarctic Oscillation on austral spring precipitation in Southeastern South America. And this research can also reflect some of the asymmetry feature of this phenomenon. And we select the region in this area. And the reason that's why we select it, it is because for this area, it covers a lot of people there. And so the precipitation is very important for the agriculture and the society. And also we could see from the figure below that it's a precipitation during the two different periods. And we could see that the deep blue bar is the average precipitation during the period after 1979, and another light blue is the period before. And we could see that this increased trending. And also this area is reported as the obvious increasing trend. And from the previous research, people find that the ENSO has an impact on these regions on the precipitation. So that means when El Nino occurs, it can be rainier, and when La Nina occurs, it's opposite. And also some researchers previously, they did the research to focus on the ENSO and the AAO's combined impact on this area's precipitation. But they just rely on a very simple correlation analysis, and they do not differentiate between the El Nino events and the La Nina events. And here we conduct the composite analysis. And then we find it's quite interesting that for the El Nino events, the Antarctic Oscillation does not do anything for this teleconnection or for this impact, but for the La Nina events, we could see this very obvious difference between these two groups. And by the way, why we select this Antarctic oscillation, because this is the most important atmospheric circulation for the southern hemisphere, and also it has a very close relation to ENSO. And then because the previous result is based on the statistical method, even though all these results passed the significant test, we also want to figure out what is the explanation behind. And first, we analyze the moisture variation, because we know that for the precipitation, the moisture and the convection are very important for the rainfall. And we first have this vertically integrated flux of water vapor, and we use this box model and to calculate the moisture transportation in two directions, that is the zonal direction and the meridional direction. And from the figure, and from this figure, we could see that the green bar is the net moisture in this area, and we could see that it is a meridional direction contribute most of the moisture in this area. And also we could see some difference between the two La Niña groups for this meridional component. And then we just select this meridional moisture transportation and calculate the correlation between it and the precipitation. And we find a very strong correlation between them. So it means that it is the meridional transportation that contribute most. And then we just select all the ENSO years, and when the Antarctic oscillation is at its extreme phase, and we calculate the cross correlation between these two indices and the IVT anomalous in El Niño years and La Niña years separately. And we find that for El Niño years, it is the ENSO signal that make the major role for this precipitation. And for the La Niña years, it is the AAO. And then we do this composite for the meridional moisture transportation and also the wind at the 850 100 Pascal level for each group. And you could see that for the two El Niño groups, actually the shading area is the IVT anomalous, and the arrows is the wind. And we could see a very clear meridional wind anomalous in La Niña groups. And because for this area, the climatology for the wind is a northerly wind. So when you see this arrows that is northward, it does not mean it's the southerly wind. It just means that the northerly wind is weaker. And then we make the difference between these two La Niña groups, and we could see this result that is quite obvious that it indeed has this difference. And the color and the arrows we show here is past the significance test. So until now, we are looking at the wind and the moisture, and these are all the low level issues. And then we also look at the upper level, because for the precipitation, you have this low level transportation, and you have this South American low level jet, but also it needs some lift for the moisture to make the convection. And then we calculate this stream function at the 200 hectopascal. And we find that for the El Nino groups, they have this trough that is a good condition for the convection. But for the La Nina groups, it is controlled by this upper level range, which can obstruct, which can be an obstacle for the convection. And also this shading colors are the OLR. And you could see also the difference between the two La Nina groups. So the conclusion is that the precipitation in this austral spring season is clearly influenced by ENSO, and also it is the strongest compared to other season. And then the La Nina, when it combines with the AAO negative phase, it is rainier compared to when it combined with the AAO positive phase. And the reason is that the meridional moisture transportation and the northerly wind and the upper level circulation all show this difference between these two groups. And so these are the main conclusions that we have for this work, and we just submitted this result to the journal, and it's currently on the review. And I will go very quickly for another topic, that's the predictability that we did before, and I will not go much details for this, just a very general introduction. That is benchmarking predictability, prediction skill in binaural El Nino forecast. So you could notice that this forecast is for El Nino, not for the La Nina. And usually the prediction are two ways. One is the forecast for the sea surface temperature and all the indices. And another is this binary forecast, means that it gives a yes or no, depend on certain indices it defined. And we are focusing on one methodology that's using the climate network and to predict El Nino. And I think that this morning Shraddha introduced a very good work of the climate network, so I will not introduce more here. And the thing is that for this prediction, the benchmarking difficult is the generation of the appropriate surrogates. And so our motivation is to create a benchmark and to quantitatively assess the predictive skill for this prediction. And you could say that we select two models that's based on the climate network, and the common spirit behind these two is that they select the nodes from different areas, and then they create the links between these different nodes and construct certain index. And then when this index is over a certain threshold, and it will give a warning for the next 1 year. And the only difference is that the region they use to base the network is a bit different, and also the indices they build is different. And our method is to shift their predictive index and to make this surrogate data set. And we check that if this shifted time series have the similar predictive skill compared to the original one, if it is similar or it's not very worse, then it means maybe the success of the models is by some chance. But if it is fails, in some sense, we could say that the original model indeed has some predictability. And then we calculate, and then after we shift the time series, and based on the similar rule of giving the prediction, we use those two. We use this shifted models and to see how their heat and false alarms are. And we use those to compare it with the original model. And for this is our major comparison is that we fit the bivariate Gaussian distribution for all this shifted time series, the heat rate and the false alarm rate. And then if, for example, the original, the heat and false alarm of the original model is out of this distribution, it means that it's a good model because it does not belong to these benchmarks. For example, if it's falls into this circle, it means that it has no difference with this shifted one. So it means that maybe they belong to the same group. And also the one quantitative variable is the distance between this original one to this to the medium of this shifted ones, and another is which area it locates. For example, if it locates in this area, it means that it has a higher heat rate and the lower false alarm. If it is, for example, fall in this area, it means that the heat rate and false alarm, the heat rate is maybe the same, but is smaller and the false alarm rate is larger. And so for this two, you could see that for this one, that it is not better than this one because the distance and the angles are all worse than this. So the conclusion is that for this one, that it outperforms compared to this model. And if you have more interest, you could read our published paper here. And so now I think that for the ENSO topic, from my own point of view, I think that the challenges is first is the ENSO in the changing climate and how it represents in the semi-models, and also how it the evolution under the climate change. And another is the prediction of La Niña, because according to my research previously, I find there are several predictions for El Niño, but actually the good prediction for La Niña are quite few. And another is this diversity and its impact. And the perspective is that currently we are still working on the ENSO's impact on extreme weather events and its economic impacts, but actually it's not easy because I just introduced the complexity of this phenomenon, and you could see the diversity problem lead to the sample size obstacle, and also how to associate to the economic risk is also very difficult, because how to match them, I think is not very easy because it can be influenced by some other factors. So that's all my presentation. Thank you.
Thank you very much for your presentation. So we have just one question, please, or two questions, not so much time. So please.
So interesting results with the Antarctic oscillation and the ENSO phases. Do you think one can find similar relationships with the Arctic oscillation and ENSO on the northern hemisphere?
We didn't check for that, but yeah, currently we just work on this southern hemisphere, but you could.
Another quick question? No? Okay. So thank you, Xinjia.
Okay, thank you.